Okay, then I will start. Yeah, hello everyone. As I just introduced, I'm Simrak, and today's topic is about quantum annealing. Yes, before talking about quantum annealing, I would briefly first introduce about adiabatic quantum computing. I believe there was a talk about adiabatic quantum computing at the earlier semester this year, but I'll just go over the very basic concept. So adiabatic quantum computing (AQC) employs the time continuous evolution, as you can see in this Schrodinger picture. And in this picture, the Hamiltonian would be the total Hamiltonian is composed of two Hamiltonians, initial Hamiltonian and the final Hamiltonian. And the Hamiltonian is multiplied by this factor, 1 minus ST and ST. Here, ST is just an interpolation or some sort of a, yeah, it's an interpolation, so that at time 0, ST would be 0, and at time t, at the final time, the ST will be 1. So in the initial state, the system will be governed by the initial Hamiltonian, and at the final state, the system will be governed by the final Hamiltonian. Okay, so the adiabatic quantum computing is a computation model based on adiabatic theorem, and adiabatic theorem is given by below. So adiabatic theorem gives us some probability with some error rate, and the probability is that the probability of the system to be in the ground state at the final time, given that the error rate is bounded by this factor. And in this inequality, G min represents the spectral gap, and spectral gap means the energy difference between the ground state and the first excited state. And if you play around this equation, you can get the T, which is the actual computation time that we need to compute in order to obey this adiabatic theorem. And if you look at this inequality, it shows that the adiabatic quantum computation time is inversely related to the spectral gap of the system. So that means that if the spectral gap between the ground state and the first excited state gets smaller, then you would need a very longer computation time. And lastly, I want to note that adiabatic quantum computing is also a universal quantum computation model, which is equivalent to a gate model, which I guess we all are a little more familiar with. And if you want to know more about the logic between how AQC can be equivalent to the circuit-based model, you can refer to this paper at the bottom. Yeah, so now about quantum annealing. So AQC is a universal computation model, but it is not practical and it's too ideal, because preparing the initial state is very hard, and also adiabatic theorem requires the system to be evolved in a closed system. But in fact, a closed system is very hard to make. So people started to think about some relaxed version of adiabatic quantum computation, and that is the quantum annealing. So in quantum annealing, the system would operate in a finite temperature in an open environment, and the annealing time or computation time is limited. So it does not guarantee the system to be in the ground state, but this is very practical. And also it is rather than more like a heuristic approach, because as I said, it does not guarantee the universality of the computation. So this is just a side note. Before quantum annealing was introduced, there was also something called classical thermal annealing. There has been some argument saying that quantum annealing is better than classical thermal annealing because in both annealing process, Uh, we slowly, gradually increase the barrier between each state. So in thermal annealing, in order to pass over, jump out of some local optima to reach the global optima, we need to introduce some heat to the system. So for example, if imagine this barrier is very tall and high, in classical thermal annealing, it would be very unlikely for the system to jump out of a local optima to reach the global optima. But in quantum annealing, we can expect some quantum tunneling effect so that the height of the barrier does not really matter. And the next is about D-Wave quantum annealer. So D-Wave Systems is the company that actually manufactured quantum annealer. And their quantum annealer is based on a Hamiltonian called the Ising model. And the picture on the top right corner is just the actual picture of the D-Wave advantage, which is the D-Wave quantum annealer. So if you look at this Ising Hamiltonian, it's composed of two Hamiltonians, the initial and the final. And in the initial, you can see there's a sigma x, and the sigma x represents Pauli X operator. So basically, in the initial state of the D-Wave quantum annealer, the system is in the superposition of state of 0 and 1. So which means that all possible states. And if you look at the final Hamiltonian, there's two terms. The first term is in first order, and the second term is quadratic order. In the first term, the H mean is called the bias, and this is how strong the effect of the single qubit is in the system. And in the second term, Ji is the coupling strength between two qubits which are adjacent. Yes, so if you look at this bottom picture, this is just like a little schematic diagram of the quantum annealer. So each quantum qubit can be in a either spin up or down state, and at the end of the anneal, it'll reach some either up or down classical state again. And also, if you look at this Ising Hamiltonian, there's a term called AS and BS. This is something we need to schedule. So this graph is provided by the D-Wave systems, and this is the default scheduling graph implemented in D-Wave system. So you can see that the AS, which represents the effect of the initial Hamiltonians, gradually goes to 0 as time progresses, and the BS slowly increases. So if you want to use actual D-Wave quantum system, you can either use this default scheduler, or you can also make your own scheduling. And this scheduling problem is also very important because there are some cases. This scheduling problem is important because the quantum effect does not last forever. There is a freeze-out point where quantum qubits lose their quantum features. So, for example, in this blue scenario, the quantum schedule was fast enough that the landscape was diversified enough so that the quantum state successfully achieved the ground state. But in this red scenario, the anneal schedule was too late, and the qubits freezed out earlier than the schedule. So in the final state, it did not really fully settled in the global optimum. So where can you use this quantum annealer? There are many applications that you can use with. For example, like there is a combinatorial optimization, which can be like a network optimization, portfolio, logistics, traffic signals, and so on. And also you can use quantum annealer with machine learning. So there are some examples or papers on support vector machine, Bayesian network, reinforcement learning, and so on. And lastly, you can also, but not the last, but this is just the exhaustive list. So one another application would be quantum simulation. So you can simulate some Ising model, many-body problems, and work Monte Carlo simulations and so on. So nextly, I would like to briefly just talk about how you can use D-wave system. So if you want to solve a model problem and solve a problem with D-wave system, there can be five important steps. First is problem modeling, second graph embedding, third parameter setting, fourth annealing scheduling, and lastly sample resolution. Each step is all very important and they all deserve their own rights. So if you are interested in a specific step, you can refer to all these papers, and there are many more. So I'll just talk about a few important steps that I think are more important. The first is problem modeling. So in order to use D-wave system, you first need to model your problem into a quadratic unstring binary optimization problem. So this is a this is a basic Cubo model in this and it looks very similar to the Ising Hamiltonian that we just saw. And also there's a technical review by this Lucas person, and this gives us a very general and broad idea how we can transform or formulate various models into various problems into Ising model or Cubo. Next is a problem embedding, or which is also called a minor embedding. What is minor embedding? So the actual D-wave quantum annealers have a specific type of architecture. One you can see on the left is called Chimera, and one on the right is called Pegasus. So if you look at the closer look at each unit cell of this Chimera architecture, you can see this eight nodes or qubits here. So each node here represents a qubit, and each edge represents the coupling between each qubit. As you can see, there's a limited connectivity. So each qubit is not connected to all other qubits, but only a few. So for example, if we think about a problem with this three nodes, actually these three nodes cannot be directly mapped into the chimera graph one to one. So what we do is called a minor embedding. We find the subgraph which can be mapped. So these yellow nodes on the left are called the logical qubit, and these are the variables from our problem. And these blue, those are called physical qubit, which actually exist on the annealer. And after mining embedding process, you can see that this logical qubit B is mapped to two physical qubits 0 and 5. And two other logical qubits A and C are mapped to two physical qubits 4 and 1 respectively. So this is the basic idea of minor embedding, and you would want to have a very efficient minor embedding. Otherwise, you would have something called chain which is very long. So in this situation, this B is called the chain of two physical qubits 0 and 5. And if you use if the problem is bigger, and if you use a very inefficient minor embedding procedure, you would likely to have a very long chain, and that would affect the problem resolution. Yeah, and this is the last slide. And the last process that I would like to mention is the sample resolution. So this is a chain of qubits that I just explained. And this is, unlike the previous example, this one has four 4 qubits in a chain. So after the annealing process, the ideal situation is that all these physical qubits have the same value. But in fact, in actual life, that does not always happen. So there are some cases when some of these physical qubits in the chain does not match the other. And that's what we call the chain break. And there are many measures to resolve the chain break. And first would be just to discard the result and anneal again. Or you could also do a majority vote, which is to say that you set the logical value of this chain to be the majority of the physical qubits value. And there are many other chain break methods, and I think you can look up some paperwork on that as well. And also there's something called the nested quantum annealing correction. So it's like a quantum error correction in the circuit-based in the gate model quantum computation. So it's more likely at the beginning of the anneal time you map each logical qubits into many more physical qubit in more like a repetitive way, so that you can. So even if one logical qubit is lost, you can still keep the result from the other logical qubits. And this last one is called a multi-qubit correction, and this is somewhat different from all the previous ones. So after annealing, you could have many samples, and in the sample you can actually calculate the energy of the system by just multiplying the qubit matrix and the result. So you can repeatedly keep doing multiplication and a little tweaking of each qubit values. You can gradually reach the not global, but at least some local optima. So in that sense, you can kind of do some post processing to find the local optima. Yeah, so that was the last procedure that you would take when you're solving problems with D-wave system. And I guess that was the last slide of my presentation. And yeah, thank you all for listening and coming to this talk today. And I will take some questions from now on.
About scheduling. Okay, so how does why does A and B looks like that? So what's the advantage instead of just straight lines?
So it's not like scheduling scheduled from like some sort of theoretical work, but it's more like from like all experimental work. So D-Wave, I guess like D-Wave people have conducted a lot of like sampling procedures, and they experimentally figured out that this was like in general the better scheduling. So it depends on your like Hamiltonian plus. So you also, if you want to like fine tune your experiment, you also need to just repeatedly keep doing with different scheduling and parameters.
It looks like Hamiltonian is abruptly changing.
Yeah, that's true. That's true.
Abruptly changing.
Oh, it also depends on your problem setting, but I think especially in this picture, the change was too abrupt because I guess the writer or the writer who wrote the paper just wanted to make it clear that the Hamiltonian changed. So yeah.
It's not related to adiabatic condition.
So, I guess in a sense, gradual change would be better, like you said, because in adiabatic condition, like the change should be very slow and in a closed system. Yeah, so, but also if the spectral gap between the ground state and the first excited state is like large enough, I guess the change time could be short as well. So yeah, again, I guess it depends on the problem setting, how you've created your cubometrics and Hamiltonian.
Maybe in the previous slide when you say
So, so if quantum annealing is ideal, it would be adiabatic quantum computing, not quantum annealing. So in general, quantum annealer does not give you, not likely to give you the global optimum. Yes, yes, yeah, because quantum annealer does not meet the requirements from the quantum adiabatic theory. So that's the reason why it does not give you the correct answer all the time. Right, right.
so physically, can we say that if there is a minimum value for that, response to the ground state?
Like the ground state energy.
Yeah, yeah.
I think it's more. It would be more correct to say if we can find the spectral gap between the spectral gap of the system, because when you actually formulate cubes, there are some like parameters you tend to add in order to manipulate the effect of each constraint and or the objective in the system. So if you just change the parameter, the energy would be, or the cubo formulation value would be different. So I guess minimum energy would change in that case. But more correct way is to say that, or it would be more ideal to find the formulation or the parameter setting that gives you the largest spectral gap in the system. Then you would have the, because you're not trying to find the energy value, but you're trying to find the solution variable. So yeah.
Okay, so about Cubo, okay. Yeah, I know that you can solve the problem with SDP transition.
Right.
So is there reference that compares the and
Uh, I think there would be likely some comparisons, but as far as I know, yeah, I didn't get to see any comparison between SDP and the yeah quantum annealer here. Yeah, it was more like the comparisons between like quantum annealer and simulated annealer, or like difference between like different kinds of quantum annealers. Yeah, those are the comparisons that I came across.
lastly, one of the example Annealing can solve it. There is SVM and some machine
Oh,
learning.
yeah, right.
So, but they're using a continuous kind of Boolean there. So how does it work?
Yeah, so regarding that, I personally been only done combinatorial optimization with quantum annealer, but there's also a way of doing some like discrete value optimization with D-wave system. So I guess that's could be a way to do it. And also, if you look at the SVM formula, it's also the quadratic, like so that's like how you formulate Cubo out of the SVM formulation. So yeah, but I'm not really sure about the continuous value variable. Yeah, that part.
In machine learning, they also use like from the finite energy state.
Right. Yeah, there are like many other applications which are not on the list here.
Okay, so thank you for the presentation.
Yeah, thank you.
There's no more question. Let's take 5 minute breaks and we'll continue.